All right, so let's talk about these. So the first one it asks is how many hours did it take her to make it from Rock Falls to Maple Park? How do we do that? Well, yeah, first we got to find the minutes, right? So there were how many minutes? 48? All right, and then divide it by 60. 60 minutes in an hour. What'd you get? 0.8 hours. Okay. And then it asks for her average speed between Rock Falls and Maple Park. How do we do that? Yeah, her distance traveled divided by the time. And so her average speed distance was what, 55 miles? Divided by her time, which was 0.8 hours. So 68.75 miles per hour. Okay, so that was the change in her position or her distance divided by the change in her time. Okay, we also refer to that as algebra slope. Okay, it's rise over run. That's what it is. We just did some algebra slope right there. All right. So then it says, if the speed limit is 70 miles per hour, is it possible that she could have been speeding at some point during that time period?
Yes.
Yeah, I would say so. Okay, if the average is 68.75, then probably there was a point where she was going higher than that, lower than that, like to average out. I don't know about you, but I struggle to stay at constant speed when I travel.
Cruise control.
Right? Oh, cruise control. Yeah, I don't like my cruise control. At times it feels like it takes me way too fast up on somebody. Like, anyway, it's just a personal preference. Sorry. Nope, not that. We would say, get a pencil. So we would say yes. Probably went faster or slower at times.
I don't like pressing things I don't really do exactly.
My car beeps at me all the time and it freaks me out. So, okay. So then we switch to the other page and it says, so because of that, do the police officers have convincing evidence from the Easy Pass alone that she was speeding between Rock Falls and Maple Park? No. Okay. They can't prove it because like Parker just said, could she have gone a constant speed? Yeah. If she could have used cruise control to stay at constant speed. Okay, highly unlikely, but possible if she used her cruise control that she stayed that constant speed. So then it says, all right, well, let's do the same thing. How many hours did it take her to get from Maple Park Plaza to the Elmhurst Plaza? So that was how many minutes? Was it 28 or 29? Okay. 28 minutes. And we divide that by 60 minutes for an hour. And what was my hours? I actually don't have this answer.
0.4666.
We'll call it 0.467. Okay. And then again, we want her average speed. And so how far did she travel? 40 miles. And we're going to divide that by that 0.467 hours. And what does that give me?
85.71
miles per hour. Okay. So now, do they have convincing evidence from the Easy Pass that she was speeding somewhere between Maple Park and Elmhurst? Yeah. Okay. That's a lot higher than 70. I'm going to go with, yeah, they probably do.
Just round down.
Yeah, just round down.
The real world is fuzzy though because the interstate could make a curve there.
It could.
Exactly.
There could have been, like, it could have been downhill. Like if you're coming off the plateau, you pick up speed as you're coming down the plateau. Sometimes you'll be 90 and be like, oh, sorry.
I would have let him.
Like it happens. Okay? It happens.
Assuming that she's traveling in a straight line.
We are assuming that. They didn't tell me any different.
Which is
So
a very presumptive assumption.
it is. Could be that she's in Kansas. That would be very flat. Okay. All right. But we could say yes. More than likely, we could say yes. All right. If the average was 85.714 miles per hour, she was probably going over 70 at some point.
Leanne must have been listening to like Freebird or something.
Yeah, when you get that right song, you know how it goes. One of my mom's best friends, this is so funny, got pulled over for speeding, and it was all because of the praise music she was listening to at the time. So her and Jesus got a little fast. So we laugh about that. She died was it last year? Yeah, it was last year about this time. Anyway, we miss her. She was something else. Bless her. She was just one of those people that didn't pay attention to what she was doing. She had surgery, and so she was on a lot of pain medicine, and the UPS man came to the door, but he had a trach. So he would touch his throat every time he talked, and she wouldn't. So because he was doing that, she started doing it when she was talking to him. I was like, Mama T, you cannot do that. Anyway. And then one time their house got rolled because she raised 3 boys, and she walked out. She went, oh, it snowed. Like, I'm like, nope, toilet paper. They did a really good job. Okay. So now we look at, must there have been a moment when Leanne was driving exactly at her average speed? What do you think? Yeah, I think so, right? Because even if she drove mostly above and below that average speed, she couldn't just skip over that speed, right? At some point, she'd have to hit that speed. So we would say, yes, she would have to hit that speed. Oh. And as Parker just said, that implies that that rate of change is continuous. Okay, so congratulations, you just did a practical application of what we know as the mean value theorem. Okay, and what the mean value theorem tells us is that if we have a function that's continuous and differentiable, all right, there's got to be a place where my rate of change at a moment, my instantaneous rate of change, has to equal my average rate of change, okay? So just like Leanne, at some point, she was driving 85.714 miles per hour, okay? We don't know what that point is, right? That was her average speed, but there had to be an instant where she was driving that speed. So when we talk about instantaneous rate of change, what are we referring to? The derivative, okay? So where our derivative, our instantaneous rate of change, is going to equal our average rate of change. So mean value theorem for derivative, here's your formal definition. If a function is continuous and differentiable, okay? Why does the and differentiable part have to be in there? I got to know I can take the derivative, okay? So if my function is continuous and differentiable, okay, and actually it says this. It closes it for continuity and leaves it open for differentiable, all right? Not as important, but then, all right? So that's the qualifications. Those things have to be met, okay? We have to be continuous on that domain, all right, somewhere from A to B, and we have to be differentiable within that domain, okay? Not worried about the endpoints, but in between the endpoints, okay? Then there is at least one point that we'll call C in that interval where f prime at C, so my instantaneous rate of change, equals my average rate of change, f of B minus f of A over B minus A. You'll hear me refer to that as calculus slope equals algebra slope. Okay. This is instantaneous rate of change, average rate of change. Those look like names of cars. In order for the mean value theorem to apply, those two conditions at the top must be met, okay? If they're not, then we're not guaranteed for that to happen. Doesn't mean it wouldn't happen, okay? But we're not guaranteed for it to happen, okay? So these are existence theorems. So let's just look at a picture. All right, let's take a function. I'll call this A, we're gonna call this B. And let's just get something cute in here, something like that. Okay. So what this says, all right, is that if we do the algebra slope, in other words, we do the slope between the endpoints. Okay. So that is my average rate of change. Okay. There's going to be a point somewhere in that, okay, where I'm going to have a tangent line that's going to have the same slope, okay? And so we could kind of sketch that out and see it. Probably going to fall somewhere right around there. We'd call that point C, all right? Where F prime at C, my instantaneous rate of change would equal my average rate of change. So if we're thinking graphically, okay, the slope between the endpoints, there would be a place where the tangent slope would match, okay, which is my derivative. So what we're going to do to start is look at some functions, all right? Do they meet the qualifications for the mean value theorem? Okay, mean being average. Instantaneous rate of change equals average rate of change, right? It's hard to get back in math mode. I have thought this much about school since I've been gone. I hope you did the same. Did y'all have work for any other your other classes? Oh, sorry. Government. Sorry. That's okay. Okay. All right, so let's look at a few and see if we can figure out, does the mean value theorem apply? Okay. So let's look at the first one. It says, does the graph satisfy the hypothesis of the mean value theorem? So let's talk about the mean value theorem. What is the hypothesis? The hypothesis is continuous and differentiable. Okay. All right, this one is continuous, but it's not differentiable. Where is it not differentiable? At the cusp. Okay, so it's not differentiable right there. Okay, so this one's a big fat no. Okay, can't do it. All right, so it. Well, it didn't. Oh my gosh, Garrett, I'm not ready.
Yeah, but it also doesn't specify from 0 to 2.
There's no specification here.
Okay, I'm assuming it means the entire graph. If it doesn't give you a specific domain, let's go with the whole thing. Okay. All right, so let's take a look at the next one. All right. Does the graph satisfy the hypothesis of the mean value theorem? Is there a value C where the derivative equals the slope of the secant? What do they mean by slope of the secant? That's the average rate of change between the endpoints, okay? So if they ever say slope of the secant, that's the average rate of change between the endpoints. Okay, so just as a clarification, if you see that phrasing, that's what they're referring to. All right, what about this one? Okay, now let's talk about where continuity has to happen. Okay.
It's closed for it's.
It is a closed domain for continuity.
So
the endpoints have to be continuous too, right?
Right.
I thought you said the endpoints didn't matter.
Endpoints don't matter for differentiability,
Just for
okay?
continuity, that's the word.
All right, so this one's a little tricky, all right, when we're looking at it in terms of the mean value theorem. We've got a discontinuity right there, okay? But if we think about the hole is filled, all right, we're going to actually say that this meets the continuity requirement, okay, because of that endpoint being filled. Now, if that endpoint was not filled, meaning they didn't have a dot down here, then we would say that it did not meet continuity, okay, which is weird. It's weird, okay? It's weird. So this one's actually going to be a yes for continuity. We don't care about the endpoints for differentiability, right? So is it differentiable everywhere else? Yes. And so this one would actually meet the requirements, okay? So this one would be a yes for the mean value theorem. When we do this algebra slope, it would be between this point and this point, all right, for my average rate of change. And so is there going to be a place where the tangent slope's going to match? Yeah. Okay, so this would be my instantaneous rate of change. Okay, so that one's a yes. That one's weird. Okay, so I just wanted you to see that because it looks a little strange. Okay. Okay, let's look at number 5. Another way to think about that, number 4, is every x value met with a y value between 0 and 4? Yeah. Okay, so that's why we can say it's continuous, which is weird. All right, which is weird. All right, look at this one. It says create a graph that's continuous from 0 to 4, but not differentiable on 0 to 4, but there also exists a point C where the average rate of change equals the instantaneous rate of change. So it may not meet the requirements of the mean value theorem, okay? But we could still find it. All right, play with that a little bit. What do you think that might look like? When I think about something being continuous and not differentiable, I think cusp, I think corner, something like that. Okay, it's just usually one of the easiest things to illustrate. So I might do something like this, okay, as my picture. All right, it is continuous, but it's not differentiable there at that cusp. Okay, but if I think about the slope between the endpoints, is there going to be a place where the tangent slope would match it? Yeah, okay, probably somewhere up through here. Okay, so where my instantaneous rate of change would equal my average rate of change. So just getting you used to what that looks like visually if you see a graph. Okay, so got to meet both requirements. And then let's get into how we actually calculate that C value. Where is that magic value where the mean value theorem holds true? Okay. All right. Okay. All right, here we go. Okay. So on number 6, it's just show that the function f of x equals x squared satisfies the hypothesis of the mean value theorem on the interval from 0 to 2. Then find the value c the theorem says will exist on this interval. So let's just think for a second what that means. All right, so my function is x squared. What does that look like? It's a parabola, but it only wants it on the interval from 0 to 2. And so if we graph that, 0, 0, 1, 1, 2, 4, so it would look like this. Okay, so is it continuous and differentiable? Yeah, okay. A simple sketch shows me that it meets all the requirements. All right, so now we want to find that value, okay? So let's start with the algebra slope. Okay, so we're going to do f at 2 minus f at 0 over 2 minus 0. All right, we're going to do the average rate of change. Okay, which is my algebra slope. If we do that, what's f at 2 in that function? 4. F at 0 is 0, and so 4 over 2 would give me 2. All right. The next thing we want to find is that instantaneous rate of change, or the calculus slope. Well, that's the derivative. Okay, that's f prime. All right, and what is f prime at x? 2x. All right, so basically we're saying there's some value c that we're looking for where these two things are equal. Okay, that's what the mean value theorem says. And it says c, so I'm going to say 2c equals 2. All right, what's that c value? 1. And that's all it's asking me to do. Okay, so if it's asking you to find c, that's what you're going to do. You're going to do the slope between the endpoints. You're going to take the derivative, set the two equal to each other. All right, that's the process for the mean value theorem. Algebra slope equals calculus slope. All right. Let's try the next one. All right, I'll let y'all play with this one. Okay, so it says let f of x equal the square root of 1 minus x squared. A is the point -1 f of -1, and B is the point 1 f of 1. Find a tangent to f in the interval, okay, -1, 1, that's parallel to the secant. Oh gosh, parallel to the secant. How do I know this is mean value theorem? Do what? Because I told you it's in the right lesson. Yeah? Okay. What's this graph look like if you graph it, by the way? Anybody know? It's a semicircle. Did you get the derivative? It was chain rule. How would I solve that bad boy? In order for the whole thing to equal 0, what's the only part that has to equal 0? The top, okay? Only the top has to equal 0 for the whole thing to be 0. And so it's going to happen when C is equal to 0. Now, I want you to go back and look at the actual question, okay? What's it asking me to find? A tangent, okay? It's not asking me to find where it happens. It wants the tangent line equation, okay? So we know the x value where it's going to happen. It's going to happen when x is 0, all right? So if I'm going to write the tangent line, I need a point and I need a slope, okay? I need a point and a slope. Well, the point where it's going to happen is that value, 0, comma. How would I get the y value that goes there? Plug it into the function, so f at 0. So it happens at 0, comma 1, okay? Now, what does the slope have to equal at that point? It has to equal 0. It has to equal my average rate of change, which we already found was 0. Okay, so my slope is 0. And so when I write that tangent equation, y is going to equal 0 times x minus 0 plus 1, or just y equals 1. So that's your final answer. Okay, so a little bit more involved. We do the same process, but it's just a little bit more involved. Okay, question on that? You sure? Okay. All right, let's look at the next one. I like this one as well. Okay. This one says, tell me why this function does not meet the conditions or the hypothesis of the mean value theorem. Okay, from -1 to 1, which means there has to be an issue. Okay, there has to be an issue. Right? What happens when we take the square root of x squared? It just equals x. But the problem is, what kind of x could it be? Positive or negative. So I'm going to rewrite this as absolute value of x plus 1. Okay? So if you think about an absolute value function, what does it look like when you graph it? It's got a corner, right? This one will be moved up 1. Okay. And so if I'm talking about the domain from -1 to +1 on this function, it's not differentiable at x equals 0. Okay. So those are just some explanatory type questions, all right? Now, let's get into what the AP questions look like. All right, let's get into the AP questions. That's what I've got left for us to do. These are all pulled from AP tests and release free response and multiple choice and all that good stuff, okay? Because I want you to see how they're going to test you over it, all right? Which is what you can expect to see on your quiz that's coming next week. All right. So let's take a look at this one. All right. Notice this is a free response question. Which part is this one? D. Okay, so it's asking you to do a whole lot of other things, and now this is part D. More than likely, this is a part that kind of stands alone, and the others probably work together for something else. And this is a part that's just independent of itself, which they will do a lot. Okay. All right, so the continuous function of f is defined on the interval from -4 to 3. The graph consists of 2 quarter circles and 1 line segment as shown in the figure. Okay, so it's very specific. Find the average rate of change of f on the interval from -4 to +3. there is no point C in that interval for which f prime of C is equal to that average rate of change. Explain why this statement, if it was like a double negative, does not contradict the mean value theorem. Okay, so it does not contradict the mean value theorem. Okay, so let's go back and look. First thing it wants me to do is to find the average rate of change. Well, it gives me a graph. Okay, so basically what I'm looking for the average rate of change is going to equal f at 3 minus f at negative 4 over 3 minus negative 4. Okay, can we calculate that from the picture? Yes, because it gave me points. Okay, so let's do that. What is the value of the function at 3? Negative 3 minus the value of the function at negative 4. Negative 1 all over positive 7. Okay, so that numerator is going to end up being what? Negative 2 over 7. Okay, if that's all you could do, you'd probably get a point. Okay, so sometimes we take what we can get, right? Like, because you're going to be tired when you get to these. All right, we will take what we get. All right, but now let's talk about why it does not contradict the mean value theorem. Okay, what does it mean for the mean value theorem to work? It has to be continuous and it has to be differentiable. Okay, we're definitely continuous, but what's the issue? Yeah, we're not differentiable right there at x equals 0. Okay, and so this is what we would say. Okay, the statement does not contradict, because they're saying, hey, the mean value theorem doesn't work. That's what they told us. It does not contradict the mean value theorem because f of x is not differentiable. Okay, and actually it talks about the domain. So we would say on negative 4 comma 3. We don't have to tell them where. Okay, we just have to tell them, yep, it's not differentiable in that domain. Okay, and you could even say at x equals 0 if you wanted to. Like if that makes you feel better because you know that's where it's not happening. Okay, yeah, you just have to prove it. What was the issue? Okay, why does the mean value not work? It's not differentiable. All right, and again, you've probably done a whole lot harder calculus in the top part of that problem, and you get to this one, and you're like, I don't even remember the mean value theorem. Okay, but that's really an easy question to get 2 points on. All right, what do you think? Okay, all right, let's look at a multiple choice question. This is actually in a calculator section. How do I know? Because of what it's numbered. It's numbered 89, which is weird. You do not have 89 questions. Remember, they change the numbering at a certain point so you know when it's calculator versus non-calculator. Okay, so let's look at what it says. It says the function f is continuous on negative 2 to 2. And it tells me that f at negative 2 and f at 2 are equal to 0. So in other words, these are my ordered pairs. Negative 2, 0 and 2, 0. Okay. If there is no c value, all right, on that interval for which f prime at c equals 0, which of the following statements must be true? Okay, which of the following statements must be true? All right, the derivative is greater than 0, the derivative is less than 0, the derivative exists, but the function's not continuous. For some value between negative 2 and 2, the derivative does not exist. What do you think? There's a lot of options there to think through, okay? Do we know that the derivative exists at that it equals 0 at some point? Yes, okay? So we know it equals 0 at some point. What is the algebra slope over here?
0.
It's 0, all right? 0 over, would that be negative 4? Which would be 0, okay? So we know the derivative equals 0 and the algebra slope equals 0 at some point, okay? They told me the function was continuous. All right, so is D a possibility? Well, and it talks about the derivative being continuous, and we haven't said anything about the derivative being continuous, okay? So we know that can't be it. We don't know for sure what the derivative is, if it's greater than 0 or less than 0, so that's not what the mean value theorem says, okay? In order for the mean value theorem not to work, which part of the hypothesis was not met? Differentiability, okay? And so the only one that deals with non-differentiability is E. There's some point in there where the derivative doesn't exist, where we cannot take the derivative, okay? Differentiability fails. And again, you don't need a calculator to do that question, okay? But that's the section more than likely it's going to show up in. You're going to find most of your theory-based questions are in the calculator section, right? Question on how I thought through that one. No, you good? Okay, let's look at the next one. 2 is multiple choice. Gives me a table this time. Okay. So it says that the function f is continuous and differentiable on the closed interval. The table above gives selected values of f on this interval, which of the following statements must be true. Okay. What do you think? Lots of options here. Okay. It gave me selected values. It didn't give me all values. So because it's continuous, are those ordered pairs that I see the only ordered pairs for this function? No. Okay. Is it possible that it does something crazy between 0 and 1? Yeah. Okay. Very possible. All right. So can we be guaranteed a minimum or a maximum just based on the ordered pairs themselves? No. And we're going to learn more about that this chapter. Okay. The function's greater than 0 between 0 and 4. That's true. All right. But does it have to be true? No, because there's a lot of points we don't know anything about. Okay. All right. So now it tells me that the derivative is less than 0 between 2 and 4. Okay, well, let's calculate it. The only way we can do an instantaneous rate of change is an average rate of change. And so let's just check it between 2 and 4. All right, just to check. So that gives me 2 minus 4 over 4 minus 2, which gives me -1, which is less than 0. Okay. If we try the next point, all right, let's say between either one of those, doesn't matter. We can just play 2 minus 3 over 4 minus 3, -1 over 1. Okay, that's looking good, but what's the only problem with that?
Do something crazy.
It could do something crazy between those points that I can't see. Okay, I only have the points I'm given, and because it's continuous, there's a lot more points in that table. So as by default, E is my only option, and y'all, that's the mean value theorem. Now the question becomes, where did this derivative equal 0? Well, if we go back and we look at our table of values, okay, are there 2 points we could use where the derivative would be 0? If the derivative is 0, that means that endpoint slope, the average rate of change, needs to be 0. So let's check it. Okay, let's check the average rate of change. So that would be the first and the last point. So 2 minus 2 over 4 minus 0 0 over 4, which is 0. So that's why it has to be E. Okay? Because it would have to be that the slope between the endpoints, average rate of change, would equal the derivative at some point. Okay? Question about that one? All right, very much these are thinking questions. Can you meet the requirements of the hypothesis, the conditions of the theorem, so that we can prove something else is true? All right, let's look at these last two. Okay, these came from portions of free response questions. Right. The height of a tree at time t is given by a twice differentiable function h, where h of t is measured in meters and t is measured in years. Selected values of h and t are given in the table above. Okay. If a function is differentiable, what does that also mean? It's continuous. Differentiability implies continuity. So we know h of t is continuous. Okay. So now we've met the qualifications of the mean value theorem. Okay. We've met them. So then it says, explain why there must be at least one time t between 2 and 10 such that h prime at t equals 0. Okay, or equals 2, sorry. All right, so let's go back and let's look at our function. All right, let's look at our function. Are there 2 points up there where if I did the algebra slope, because they gave me the calculus slope, where the instantaneous rate of change would equal 2? Three and 5. Okay, if we look at those 2 points, 6 minus 2 over 5 minus 3 gives me 4 over 2, which is 2. Okay, so now how do we explain that the mean value theorem works? Well, here's what we say. Differentiability implies continuity. Okay, therefore, h of t is continuous on 210 and differentiable on the open interval. Okay, so we've met the hypothesis of the mean value theorem. Okay, so then we finish it off by the mean value theorem. H prime at t equals 2 on the interval from 3 to 5. Okay, so we state where that slope occurred. Okay, we state the interval where that matching slope occurred. That's it. Okay, this would probably be worth 2 points. One for the conditions of the mean value theorem and those purple words, and one for the last part in green. Let's do one more. Okay, so practicing with the reasons, it's important. All right, it's important. It's going to make the difference between a 4 and a 5, a 3 and a 4, 2 and a 3. Okay, when it comes to your test. All right, rock and roll, last one. Okay. So it says let G be a differentiable function, and it gives me this whole big chart of values. Okay. Is there a number C in the closed interval from -5 to -3 such that G prime at C equals -4? Justify your answer. Okay. So here's the clue that we're doing mean value theorem. First of all, it tells me G is differentiable. So if G is differentiable, G is also continuous. Okay. It gives me a closed interval from -5 to -3, so I'm only looking at the top part of the table. Okay. It also gave me an instantaneous rate of change. All right. So do I care about the derivative column in this table for mean value theorem? No. All I care about is the average rate of change. Okay. So is there a place, all right, so now let me take that back. What would I have to check to be sure that the mean value theorem applies? Okay, we know it should. What should also be true? There should be an average rate of change that is -4, okay? And it should also be, it should just be the endpoints, okay? Because we've got the instantaneous rate of change. The average rate of change is going to come from my endpoints, so let's check that. All right, so I would do f at -3 minus f at -5 over -3 minus -5. And we've got those y values. So 2 minus 10 over plus positive. Is that 8? Did I do it backwards? No. That's 2. Bless it. It's been a day. Okay. So 2 minus 10 would be -8 over 2, which is -4. Those two numbers match, so we're good. My slope between the endpoints matched my derivative that they gave me, all right? So is there a number C? We're going to say yes. Okay. G of x is continuous and differentiable. On -5, -3. And then by the mean value theorem, okay, f at -3 minus f at -5 over -3 minus -5 is equal to -4. So G prime at C equals -4 on -5, -3. Okay, so yep, it's true. Okay, it is true. That average rate of change would equal the instantaneous rate of change on the interval. All right, so you're basically restating the mean value theorem every time. Okay. Okay. So your assignment, your practice, all right, there's a worksheet back there. It's the check your understanding from the activity and then a couple of problems out of your book. You can just look at, I put it all on the same worksheet, homework 5.1. But on page 217, it's 1 through 13, the odd ones. That's just having you go through and practice finding that C value. All right, finding the secant slope, finding the derivative, setting the two equal. There's some interesting problem solving in some of those you might want to look at, okay? And then there are 3 problems from the check your understanding. One's a table, one's a graph, and then one's just showing that the mean value theorem will apply, okay? All right, do your wrap up on Google Classroom real fast so that you got that done, and then you can look at your superlative email, all that good stuff. Okay. Good job. Welcome back. I know. Well, the good news is you don't see me again until Wednesday. That could be bad news, though, but
That is bad news.
okay. Sorry.
Bad news, I'll miss you so much.
Smiling face brightens my morning.
Oh, well, you can walk by. I'll go, and then you can go a second walk. Actually, I probably won't even be in here. I'll be setting up for testing tomorrow.
Oh,